My name is Arndt, and I'm the first presenter in today's session. So we're going to be covering custom tube bending and laser cutting, getting it right. Alrighty, a little bit about me, not that you guys care all that much about it probably, but my background is kind of started out in engineering and design right out of high school, went into technical college locally and got my associate's degree in mechanical design. From there I kind of worked into a couple different internships and worked with a small engineering firm developing new products, some small things, but also worked with some OEMs making some big drawing packages and things like that, primarily detailing and design. That kind of moved into testing and small scale manufacturing, and then got me into a position where I am today, doing tube and pipe engineering and fabrication, working for a company that does strictly tube and pipe fabrication and laser cutting. So that's kind of what got me in, a decent fit for the topic today. Early career experiences, when I first started out in the tube and pipe world, I did estimating and simulation for laser feasibility and trying to give estimators laser times, and I actually quoted myself getting out some basic laser jobs. And currently, my role is kind of still looking at feasibility, making sure that anything that is coming through the door, we're going to be able to get out to our customers in a timely manner and meeting quality requirements. I make programs and production prints for our tube bending department, our tube laser cutting department. I also kind of am cross-trained as far as an operator on just a couple of our tube laser machines. Whether it's 3D cutting or inline tube laser cutting. So also, kind of play into inspection as well. We'll kind of touch on how that all comes together. But that's about it for me. So before we get started here, how many people are familiar with tube laser cutting? Sounds good. And then, how about tube bending? Sounds good. All right. Anybody brand new to these areas? Perfect. Hopefully you get something good out of it. I'm just going to make a statement too while we kind of go through everything. If there's questions you guys want to interrupt, feel free to. There's no need, in my opinion, to kind of wait for the end of it. It'll kind of bring up good conversation, and there's not a whole lot of people in here that are brand new to the area, but I think that'll be beneficial. All right, so kind of what we'll cover is applications. Applications just as far as some things that tube and pipe, either bending or laser cutting, go into. Just about everywhere. The chairs you're sitting in is a great example. I say that all the time to anybody that's asking where you use tube and pipe. You pretty much just look around. As you guys know, being familiar with it, as soon as you get involved in that industry, you see it everywhere, and it kind of changes your perspective on a lot of things. We'll talk about some raw materials. Raw materials being the material, the substrate before it actually becomes that finished product, whether it's bent or cut. We'll talk about tube bending and the tooling that goes into it. A lot of people, that have experience with tube bending understand that tooling is very critical in that. Laser cutting, we'll have a section on laser cutting. Pre and post bending, I kind of touched on that before with having the multi-axis. Yeah, go ahead.
So you talked about it a little bit, but how do you bid it? How do you come up with the pricing for a job? You set up a set thing and then you explain.
I guess is what type of job are you talking about?
Laser cutting, just flat.
So I don't particularly do a whole lot of flat laser cutting as far as quoting.
Okay.
Primarily tube bending or tube laser cutting. So as far as that goes, you really need to look at how long it's going to take, to cut your parts, and however you need to yield depending on the quantity of the job. You got to figure out.
Yeah, I just didn't know if you had like a set price. Like if you had 100 pieces, it
Oh,
took you
sure.
an hour, or you had 10 pieces, it took you an hour. Would it still be the same price?
Because
it's still an hour.
Sure, I understand.
But the cost per piece would go up for the customer.
Exactly, right. So
And
that's
you did that. That's all.
we do. Where I work, we have kind of a universal, hourly rate for that machine, and depending on the complexity of the job, we're going to have a setup rate.
Yes, sir.
So if it's, if we figure an hour setup, that's all factored in, and like you said, it'll get dispersed across the quantity and lower the piece price as you go. So that's our very basic starting point is, working off of that initial setup.
Yeah, that's the way I was thinking about it. I just didn't know if that was the wrong way of thinking about it.
Sure, that's how we've been doing it. We're not a very high volume production shop, but so we really have to cover our bases that way. So we make sure setups accounted for. All right, so coming back from that, we have software and machine control. We're just going to touch on that a little bit as far as the software to run these specific machines, whether it's the CNC tube bending machines or laser cutting machines, and kind of how they all translate from start to finish. And then challenges and benefits. Obviously, with anything in manufacturing, you're going to run into issues, and once you overcome those issues, ideally you'll have some benefits. You'll be making money and getting jobs through the door. All right, some generic industries that this can go into would be aerospace. There's bent tubes all over, like we mentioned, and aerospace would be a great example of one of those. Fuel lines, hydraulic lines, things like that. Agriculture, again referring to very common everyday things, would be railings and catwalks, stair sets, things like that. Going down to framework, just about anything in a fabricated metal assembly. You could really utilize laser cutting and tube bending. Auto truck and trailer, kind of the same thing. Framework is very heavily reliant on tubing and laser cutting in these days. Truck and trailer, again, frames on all these items. Lines, like I said, hydraulic lines, fuel lines, things like that. Fabrication in general, most of these components, whether they're bent or laser cut, go into some kind of fabricated assembly. So very general fabrication. Food and beverage, again with lines. Anytime you're transmitting fluid, a tube is a great way to go, one of the only ways to go. And then marine applications, very similar to everything else. Anything is going to require those fluid transfers and structure, things like that. It'll all be potentially could be bent tubes and laser cut tubes within these assemblies. Another thing, to touch on, bringing the raw materials into these specific applications is, depending on the environment that each of these potential tube or products are going to be in, you're going to have to look at what exactly you have for a material going into those environments. Then recreation, again, very common one. You look at playground equipment, things like that, monkey bars, bent tubes, very generic. It could be very simple, it could be very complex. You basically see bent tubing everywhere. All right, so like I was saying, touching on raw materials, the first thing you need to do is obviously get the material to make the parts. So that's kind of a challenge these days. To your point before, as far as quantity goes, that can play a huge part in that. You may be able to source it direct from a mill, or you might have a local supply house. It all depends on the quantity that you're looking for and who supplies the materials that you need. So kind of types of raw materials, your general stainless steel, aluminum, all that can be laser cut, as well as some of the red metals, bronze, brass, copper, things like that. Those can all be bent as well. Most of the time we're looking at round and rectangular sections, but it can vary. You can have custom extrusions that can all be cut and bent as well, depending on your machinery and your tooling. Challenges and characteristics, everything's going to have their challenges. It could be the material size, the material itself, the material properties, the wall thickness, the outside diameter, things like that make, definitely specify your equipment and specify what all has to go into making parts like that. Applications and material types, again, we kind of talked about having specific material types per your application. Again, you're looking into something that might be underwater or in a salt spray environment, something like that. You might want to have a real high corrosion resistant stainless or something like that. So you basically want to source your material for your application and environment. Some very common tube bending methods are rotary draw bending, freeform, and multi-radius bending. Rotary draw bending is definitely going to be your most straightforward bent product method. I'm going to show you a video here about a basic CNC controlled all electric rotary draw bender that is actually a manual bender as well. It's probably the most simplistic out of the three shown here. Like I said, most of your standard tube bending is either going to be rotary draw bent with or without a mandrel. There is some that is press formed, but we're going to be specifically talking about rotary draw bending. So the gist of this is rotary because you're going to have a set of dies that rotate and pull your tube around this die to create the desired bend radius that you want. There's tooling and obviously machinery that goes into this. I got another slide coming up that kind of goes over some of the tooling and things like that. So I'll briefly describe freeforming also. Freeform is not very common, but it's something that is done a lot of times for very aesthetic parts or architectural parts, artsy things. They definitely have their place. We've had some parts that are ran through our freeform bender specifically because we don't have tooling maybe for it, and the customer needs a desired center line. That's a pretty good application for a freeform bender. You can do basically, if you were to draw a spline, it has no real rhyme or reason for it. If you can translate that, you can bend it on a freeform machine with some limitations. There's OD center line, wall factor limitations to that. But there's machinery that's come a long way too. I believe there are mandrels or machines capable of using a mandrel in freeform bending. Like I said, it's not as common, but it's definitely out there. And then multi-radius bending. Multi-radius and rotary draw bending can kind of go hand in hand. They're the main topic on multi-radius bending is that you can bend several different radii on the same part. Again, if I can show you the video, we've got a great video of a part that's a standard rotary draw bent around a hard die. Moving over to a set of roll bend tooling to create a large radius, all within the same part. So there's, I believe, 2 or 3 different radii on that completed part. That's something you can do, and that's specifically on a fully electric CNC controlled machine also. Tooling, like I referred to before, is very critical in tube bending, and most of you guys understand that. So we'll kind of briefly go over these different pieces of tooling and explain kind of why they're critical and what they're used for in the tube bending process. The first one up here, right here, is your standard bend die. this is a bend die shown with a removable insert. So this would essentially be grab on one half of the tube, and be sandwiched. The tube would be sandwiched by that clamp die there. But this is what establishes your center line of your bend radius. It basically, this center hole would go on the post of your bender, and that rotates around, and essentially when the tube is clamped in here, it pulls it to whatever degree of bend of rotation that you have that bend die making. Alright, so the next one is a clamp die, like I talked a little bit about. So the clamp die matches in this area on the bend die. This is critical for grabbing that front end of your tube so you can pull it around that bend die and get the desired center line and degree of bend that you're looking for. If you didn't have this, you wouldn't be able to make a bend whatsoever. You need to also make sure, I believe this is actually modeled with serration on it. That's just the added friction, so you can really hold on to that tube so you don't have any slipping problems. That can throw off parts completely by not allowing degree of bend. It can also create ripples and humps on the tube material itself, which is not ideal. So the next piece here is the pressure die, which is up here. So the pressure die essentially is like a long clamp die, but it's positioned on the back side of the bend tangency. So up here on your bend die, so if pretending that there's a tube that's going to be bent in this channel here, if I can figure out how to do that. So essentially there would be a tube running through here, and that pressure die would stay on the back side of this. If this was going to rotate, I guess it'd be counterclockwise in this image. That pressure die would be pushing on the tube, and like how this clamp die would be pushing this way. This pressure die would be pushing back here on the back side of this tangency. And what I'm referring to is the tangency, which would be where the straight and the bend start here. So this tangency would be at this point right here where this bend die insert meets the radius on your bend die. So what that pressure die does is it keeps pressure on the tube being bent. So basically, like a good analogy for something like this would be if you were to try to break a stick like around a tree or a post or something like that. You basically would just have, if you didn't have your pressure die, if you had that stick here and your post here, you push on one side and it's not going to do anything, it's just going to wrap right around. So that pressure die keeps that even pressure on both, so you can actually bend or break that stick around the tree or post. In this case, obviously it's a tube bending around your desired bend die. So on the opposite side of that pressure die, there is or is not, depending on your tooling setup and your desired bend. Whether if it's a thin wall material, you might have a wiper in there. If it's a real heavy wall, you might not have a wiper in there. But what a wiper does is, like I said, it sits on the opposite side of the tube as your pressure die, and it has this real feathered fine tip right here that sneaks in, it touches between the bend die and the tube itself, and the idea behind it is to wipe away any humps that may form when you're applying pressure against that bend die with the pressure die. So that's something that's very critical if you're, like I said, with real thin wall, you're applying that pressure, and that thin wall is relatively easily collapsible. So if you can stick that feathered tip of that wiper in there, it does add a little bit of extra friction in your bend, but it can prevent humps from forming on the back side of that tangency. So the other piece here, again, more critical for thin wall and tight bending would be your mandrel. And this is a piece of tooling that sits inside the tube while you're making your bends, and it essentially has, in this case, it has 3 balls. So those 3 balls kind of go along with the bend and stay inside that tube as it's being bent to keep that from ovalizing too badly, because you're going to have your tubing's going to want to flatten out as it gets pulled around that bend eye. So ideally, it kind of limits the amount of deformation, so it doesn't flatten out or you don't have marks and things like that. So if you need to have a round tube, you're probably going to need a mandrel as long as your material or your wall factor calls for it, or also your center line. If you have a real tight center line, it might be something you have to have in there depending on your material. The last piece on here is your collet. So this is an example of a collet. So it's a separate 6-piece collet, but it's just like a collet in a drill or any other collet you can really think of. What it does is it holds the material while it's being bent, before it's being bent. It kind of establishes your loading position. So if you were to stick your straight length of tubing onto your machine, it's going to be, in most cases, butted up inside that collet, clamped on, and then traverse forward so you get to your desired first bend location to establish your front tangent length. And if you tangent length, kind of like I was saying, it's the distance, or it's the straight where it meets the bend is the tangency. So we call it tangent length from that tangency out on the straight portion of it. So when I refer to the tangent, that's the straight section that's not bent, either before or after it bends. So it'll establish and control that length. And if you're doing multi bends on one part, it'll establish the next tangent length. It can also control rotation depending on the machine you have. A lot of the CNC controlled machines have, the ability to program rotation. So you might be able to make one bend, translate, make a rotation, make another bend. So now you have a bent part that's not just in one plane, like if you were to flop a handrail over, that's all a standard handrail anyways, that's bent in one plane. There's no rotation in that. But now if you have a handrail that goes down and makes a turn and goes down to another flight of stairs or a landing, you're going to have rotation in there if you decide to bend it in one piece. So that's something that a collet is really helpful in. Some of the older machines, if you're trying to make a bent part with rotation, you might have to have a protractor on it or some other kind of hard gauge to develop that degree of rotation, where with a closing collet, CNC controlled, you can make that rotation in the program and have the machine do it for you.
Your collet's typically on the back end of the...
Correct. Exactly. Yeah. So you'll have. So again, like if this was your bend eye sitting on the machine, the part was not anywhere near bent yet, you got a full straight length of tube, you would slide that in through this over a mandrel if you have it, all the way back until the end of that tube goes into that collet. And your collet would either let the tube pass or clamp up on it in the desired position. On the opposite end, it might be, your collet could be 20 feet, depending on how long your machine is and how long your part's going to be. It could be sitting 20 feet back from your point of tangency. You can slide it all the way over, clamp up on it, or you could have it 4 inches back from here. As long as there's no issues with the other tooling you have there, your collet can come up pretty close to your bend eye and your tangency there. But obviously, it gets too close. There's a lot of moving parts on a bending machine that could get in the way, but it's always on the backside. So 2 bending challenges. I kind of touched on that as far as tooling goes. There's definitely some challenges to bending tubes on tight radii, which is a lot of times we consider a 1D bend a very tight radius. Can't get a whole lot tighter than that. Most of the time, your material is your driving factor on that. If you have especially with thin wall material, your material can only stretch so much and it can only compress so much before it starts to wrinkle up on the inside or stretch or split or break on the outside of the bend. So that's a big challenge. Tooling definitely helps with that. There's only so much you can do. Your material can only stretch and gather so much. But again, with tight radius bends, your tooling is going to be really critical. You're probably going to need a wiper depending on the wall thickness, and you're probably going to need a mandrel.
What's a wiper?
So a wiper, I'll go back to this. No problem. So this is your wiper die here. This is like considered a block wiper, where it's all one piece assembly, or not an assembly. It's just a one piece solid. In this case, it looks like it's probably a bronze wiper or something like that. But so that sits on the back side of your bend die. Would be tucked in here. Like if this bend die was shown in the load position where it did not make any rotation yet, that wiper tip would come in from this side on the back. So if this is how your bend die is set up to grab the tube, it's on that same side. It's not where your clamp die is. It's not where your pressure die is, but it's opposite of the tube from your pressure die. And that the tip of that wiper is what tries to wipe away any bends that might be, or any humps, I should say, or bumps that start to get established by the force of your pressure die pushing against your pressure die and your clamp die, I guess, so pushing against that bend die, because there's obviously, if you have a straight tube in here, it's only touching in this clamp area, and it's all void on the backside of that otherwise, so that wiper kind of takes and pushes against and counteracts the force of your clamp and pressure die pushing it against the bend die. So with a thin wall tube, that wiper, like I said, is going to try to push away any of those humps that are going to try to form on the backside of that tool. All right, so that kind of a good translation to the material thickness. That definitely is going to be an issue with thin material. Thick material, you're going to have issues too. It's not quite the same, but it might be more of a strength thing or a machine thing. You're going to need to have a fairly stout machine to bend thicker material. It's all relative, but the thicker material, it's going to be easier as far as a machine setup and tooling setup in general. There's not going to probably be a wiper. There's probably not going to be a mandrel. So you're looking at the most basic tooling setup, but you can definitely have issues as far as strength capabilities and things like that. Parts with existing holes and features, that is definitely a challenge. So I don't know if any of you have dealt with that before, where you have a hole either on or close to a bender. That's where the customer wants it. That becomes a problem. A lot of times they'll either split the material because you have that relief in there. You're basically getting rid of some structural integrity of that tube. So if it's in there before you bend it and it's too close to the bend area, or it's on the bend, a lot of times you either have a lot of deformation in that hole feature, where if it's a circle, it might be a complete oval shape, or we've seen it where it actually splits and the material breaks, or that hole stretches and it's definitely not a hole anymore. So that is and I shouldn't say just holes. Obviously it would be a through cut somehow, either through one wall or both walls. Doesn't have to be a round hole, but it could be a slot or rectangle or any kind of machined or laser cut feature on a bend tube. If it gets too close to the bend area or on the bend area, you can have some problems.
How do you deal with it?
So there's several ways you could deal with this. The easiest way, not always the best way to do it, is probably to put it in after the fact. So
Put the hole in after the fact.
exactly, yeah. We have dealt with things where you have, if there is deviation allowed, where you can put it in and see how much it stretches. You can also compensate for that whole shape. So you can kind of pre-op around it if you're laser cutting before you bend it, for example. It works depending on your material and your hole size and everything, but we've definitely had success doing that.
Is there like a rule of thumb to how far you should stay away from a hole if it is pre-existing? Before you're ready to start?
I like to say at least 1 times your tube diameter, but that's very dependent on the material itself. You can get away with it too with different tooling setups. You can play with like mandrel position and things like that. It depends on how much deformation in the bend area you're allowed as well. If you can allow for more deformation in the bend area, you might not have as much stretch translating outside of that the bend area. Say it's at 90 degrees, you might not stretch that much past 90 degrees. But if you're really trying to hold the shape, it might stretch some more material in towards that bend area. So another challenge, large versus small runs. So challenges with large runs would basically just be getting your machine or your cell dialed in to produce a high quantity of parts. This can take a lot of engineering up front. You can have a lot of time and resources developed or into developing that just to get everything out efficiently. Small runs, again, back to the setup comment before, you're always going to have a machine setup, and some setups are going to be more time consuming than others. If you have a small run and it's a real complicated part, you might have hours and hours into a setup and you run it for 10 minutes and then you got to yank the setup out. So it's all, you kind of got to weigh, it's from a costing standpoint, you got to weigh, how much you're going to be able to charge for this part, how much time is going to go into it. But it also, as far as time in the shop, you definitely need to take that into consideration, because even though it's a small job, you might not have a lot of hours behind it. Your setup might be very time consuming, and it might not translate to a lot of other bends that you have coming through. So that's definitely a challenge, is trying to get that dialed in to be efficient. And part of that is just understanding your tooling setups, understanding what material and what center line needs to have specific tooling, whether it's your wiper and mandrel position, your wiper rake, things like that. Wiper rake, I don't think I talked about that at all, but that would just be essentially a rake angle of the wiper itself behind your bend die, just so you can try to get the very feather tip touching on the material in the bend die, so you don't have excessive wear and excessive friction to, again, make your machine struggle or scratching material.
Broad question. What kind of tolerance can you get to bending?
So,
I know it depends on material, but
yeah, depending
as
on
an example, like 1.25" schedule 40.
Okay.
Handrail stuff.
Sure, like if you're doing it on like a fully CNC or fully electric CNC control machine, I believe we're told 0.2 degree.
Okay.
It's probably pretty tight. That's with they have an option called laser spring back control, where there'll actually be like a little laser sensor, kind of like a proc sensor, developed into the tooling, where it'll make a bend and it'll let go. The dies will open up and it'll measure exactly how much spring back there is, and then it'll reclamp up and bend it back to a couple degrees. And
how much spring back would you predict? That like we're talking.
Sure. If it's a steel tube, hardly anything. Sometimes, depending on the grade of material, you actually have to pound them off of the bend die because it hugs onto that bend die so much. If it's a stainless part, what do you say, 1.25" schedule 40 or something like that? So something like that could spring 1/4 inch, depending on if it's just a 90, maybe a 1/4 inch if you're bending a full 180. Seen something like that spring all the way up to a 1/2 inch. So that's definitely becomes an issue if you're trying to hold center to center points on your tangencies after your bend. You might have to either go down a size on your bend die, or we've had to split tubes in half like that, but then it's not a true. It's an assembled piece, and it can definitely change your tooling. That's probably the best way to do it, although it's not always the most cost-effective way to do it. All right, so we touched on correct tooling pretty much there. Inspection, that's another challenge. Like I talked about, a standard handrail, if it's just going straight down the flight of stairs where there's no rotations or turns in it, something like that might be really easy to inspect because you can establish linear dimensions on it. Basically, like you could have even like a full scale layout. Like if it's going into a fabrication name, I already have that. Otherwise, it's easy enough on a print to add your what we call overall or box dimensions, which would just be like your max points, your high points, you know, or relative to the orientation of that part on the drawing or in its environment. But 2D parts are relatively easy to draw. That's what I'm saying. 2D referring to no rotation in the bends, and they're relatively easy to inspect that way because a lot of times you can, depending on tolerance, do it with a tape measure or on a layout table or a weld table, something like that. It gets tricky when there's rotation involved because you might be 2 bends and it might be a 39-degree rotation. And now if you lay it out on something, you have something up in space. So again, what I refer to as overalls or box dimensions, that is a really simple way to measure something like that. You basically have to use like a height gauge or figure out a way to orient that part where you can measure that rotation and that overall height of if it's a tangency on the end of that rotation coming up off the table, you're going to want to have a check dimension here too. So it makes it a little bit more complicated if it's drawn in detail correctly, or you have the equipment to inspect 3D parts like that, whether it's a CMM or something like a tube inspect. I don't know if anybody are familiar with the tube inspect, but essentially it's an optical system. It's all cameras that take a picture, and there's reference points inside. It's basically a little booth, and it optically inspects the part, and you enter in your XYZ or LRA data. So XYZ would be your theoretical intersection points between bends from the very start of and if you got a tube cut off, it'd be like a 0 point to your next point to your next point, kind of like connecting the dots out in space somewhere. So it relies on XYZ and LRA. That's another. If you have something like that and you have that data out to your shop, it makes inspection a lot easier on these 3D parts like that. All right. Anything on tube bending in general? I mean, we're going to kind of make a hard transition to tube laser cutting at this point. Yeah.
So, I have a strange question for everyone who
Sure.
knows tube bending. You may know this too. So we are all of a sudden having issues with certain materials, and it seems to do. We're having it's non-hydraulic material, so it's not pressure tested, but it is splitting at the seam after flattening.
Okay.
And so what I think is happening, and maybe you can give me some feedback on this, is so the tariffs happened, all of the material ran out, and this problem started around January, and it's specific parts that I've been making for years and years and years, and now all of a sudden it's splitting.
Okay.
So I think that the U.S. is pulling carbon out, and carbon makes the material more pliable because of emissions.
Sure.
So my question is anybody else having that issue? And as someone, you're way more advanced than I am with your company, what would you suggest we do? Because we've had different issues with different vendors, so it's not just one vendor.
Sure.
Mill. The mill it's in spec, but
Right.
there's still less carbon. And so that is my guess, and I'm a little concerned that in the future, as we're bending material and more carbon gets pulled out, industry like tube bending is going to be a problem.
Sure. So did you say that was in flattening or in bending?
Yeah,
Flattening.
so we bend it, drill it, flatten.
Okay. And it's splitting during the flattening process specifically. I mean, we've seen that. I've seen that. But it's not something that we come across very often.
Yeah.
You're getting material certs by batch.
Mm-hmm.
This inspector is showing you the actual alloy contents.
So the issue is because it's not pressure tested, you can see that the carbon is really making a difference. So there's less carbon, but it's still in spec. So that makes sense.
So surface telling you that's less carbon.
But it's still.
Sure.
So
But
you're not
sometimes,
somehow
but sometimes it happens,
being
and
more
sometimes,
aggressive on your.
yeah, sometimes it happens and sometimes it doesn't. So the only thing you can do then is order hydraulic material, which is like 3 times the cost.
Right.
Of course, you have these customers that already materials like this, and they have no way.
Yeah.
So,
It's a welded seam test?
yeah.
Where is the seam oriented?
So we've tried it in every area. We've moved it bottom, top, side, it still is doing it.
Yeah. Because that's a good point. That would be. Sorry, what's that?
Yeah, it would be.
Well, yeah, that's what it's even that, maybe a temporary process, like heating and try to realign and then.
Yeah, so the other thing is that the weldments are not, they're acknowledging that they're not getting the welds hot enough either.
Yeah.
Oh,
But still on the spec.
Right.
So anyway,
that's
anybody has
interesting.
any advice?
Yeah.
I always thought kind of your carbon content in your steel is more malleable, so it's surprising. But maybe I just don't understand steel right then. I might be
Yeah,
backwards.
so it should be, so it shouldn't be splitting.
Right.
The higher the carbon, right? So they're pulling carbon out. Does that make sense?
Right. Yeah, I was saying my understanding was you lower carbon content in the steel, it becomes less brittle, more ductile. So I'm surprised that it's splitting.
Yeah. It's interesting. Like to your point, I mean that would be my first thought is the orientation of that weld seam, whether relative to your forming process. But yeah, if you went through it,
Okay, thanks.
hey, no problem.
And then my other question was, what type of inspection equipment are you guys using in your shop for?
Sure.
The bend tube?
So the tube inspect that I referred to, the optical machine, we have several of those. Also it's essentially a roller arm, a portable CMM with a scanner. We tend to scan more than probe. Don't have to worry about fixturing so much with the scan. You don't have to worry about moving the part out of the way if it's a small light part. We get enough data off the scan relatively quickly. But yeah, that's a great question. That's if you have real complicated parts, especially parts that what we would call compound bends, where you might have a bend on a bend with no tangent between the two, that gets very tricky to measure. And that's something like a CMM is about the only way you can accurately do that, depending on what your customer is looking for. All right.
I got another question.
Yeah.
What kind of equipment would you use to make a railing for spiral staircase?
So for a spiral staircase, there
Something
are.
precise.
What's that?
If you want something pretty precise,
Sure.
because we do it like manually. We turn it in the roller,
Okay.
but it's not very precise.
Sure. Like I referred to before, machines called freeform machines. We can do spirals on a freeform machine. It's tricky to find somebody that has a machine to that size that can do it. But something like that you could. There are CNC controlled roll benders that would be able to probably do that. And if they don't turn it, I've seen it where there is another support come up to kind of force it into more of a spiral. But I would say as far as accuracy goes, if you had a CNC controlled machine, that's going to be pretty consistent. Something that I've seen with rolling on a CNC machine is higher scrap factor due to potential changes in material, or if you don't keep track of your heats and know exactly what, and you almost never know exactly what that next heat's going to do, you might take a few pieces to get, and a few is relatively lightly, I would say. So it'll take some setup time to get that dialed in. But if you can control your material, once you have a dialed in roll bend process, it should be relatively consistent and accurate.
And there's no measuring system that could measure it coming out of the roller?
I have heard of that. I haven't seen anything specifically on a machine like out of the box, but I've seen it integrated. But as far as it'd have to almost be like the depth of the tube relative to how far where that position is. So I'm sure you could do it with some kind of, optical sensor, depth sensor, or something like that, maybe. But yeah, from what I've seen, and maybe there are out there, I haven't seen anything on a machine out of the box. Anything else on tube bending in general? All right. So the tube laser cutting. Basic equipment for a tube laser would be a tube laser itself. There's two main types of tube lasers, like there are probably with sheet lasers and other laser cutting equipment in manufacturing. It'd be like a CO2 laser or a fiber optic laser. They each have their specific place, but most of what we're seeing these days are fiber optic technology, especially within the tube laser cutting. If there's some of the really thick structural steels that are considered tube laser cutting or within tube laser cutting, they might be a CO2 powered machine yet, but a lot of it's going to fiber optic. So some of the capabilities you have with tube laser cutting is, in its simplest form, is cutting lengths. If you throw a full raw 20-footer, 24-footer, whatever you have for raw material, you can cut it to essentially whatever length, longer than the width of the beam or your kerf. You might have other challenges with that. It might fall down to your scrap, and if those are the parts you're trying to hold on to, you might not have them if they're too small. But as a general example, you can cut lengths to basically whatever you want, depending on your tolerance and, like I said, feasibility as far as what's going to be scrap and what's going to be a usable part. So something from as basic as that, all the way up to maybe you don't want to bend parts and you want to notch something and have your fabricators or somebody bend them themselves and tack weld it up to act as a vent tube. Tube lasers capable of that. Obviously, putting hole features in is very standard on a tube laser. Hole features, the other thing that's handy with the tube laser is the profiles of holes that you can cut. You can't really put a part in a vertical mill and machine a square. So a tube laser, you can achieve just about any drawing or profile that you can draw. The other thing that's great about a tube laser is coping. Tube lasers, with or without like a 3D head or a tilting head, are great for coping because in most fabrications it actually leaves you a little bit of room for penetration on your welds. It copes way faster than any other manual process. If that's something that you do very often, I would say that's a great investment.
Is there a type of equipment that combines the tube laser cutting and pipe bending for just simple coping like that?
I haven't seen it in one machine. It could probably be something again that's integrated. If it's something that's bought and done after the fact. Okay. I'll talk a little bit. There's another. I don't know if the video will pop up again, but the 5-axis tube laser cutting. It's not actually bending the part, but it's cutting the part after it's bent. So it does go to another operation or another cell. But I have seen like shears or notchers at the end of tube benders before. Depends on the size. In most cases, it's like probably 1 inch OD, maybe 1.5 inches or under, something like that, where you're going to actually be able to have the machine strength to pierce and shear that material off. But I've seen that built into basically like a set of clamp guys. It'll clamp up on a part, bend it, and it'll come in and make that pierce and cut off. So I'm sure you could have that done with a cope as well. But yeah, as far as just the straight length or straight tube laser piece, coping is very handy on a tube laser. Usage and operations, again, something like that. If you're into railing fabrication, you have coping going on and things like that. That is a huge benefit to that. I touched on a 3D head or a tilt head. Most times, or most generic tube lasers are, it's strictly a vertical, the head is always vertical, so your beam is always going straight down perpendicular to the tube surface itself. We're starting to see now more and more companies coming out with a tilt capability, which most of them I've seen are about 45 degrees either way, so you can actually start to put bevels and some countersinks in holes that you're cutting directly in that machine, so you don't actually have to kick it off to a machining operation after the fact. So that's kind of relatively new, and it's a very handy feature. You can run into some issues with that as far as the angle. It's definitely limited that way, but it's a nice upgrade to some of these newer machines. The integrated software. Most of the tube laser companies right now have some very robust software that runs them. So if you have something like a 3D model, a step file, IGES file, Parasolid file, anything like that's already established, I mean, you might be able to get licenses to run, import a direct SolidWorks file or a Creo part or something like that per week. But generic 3D files, a lot of these companies you can download or not download, but you can import those files directly into that software, so you can pick on that machine as you had it modeled, where your cut features are and your order of your cuts and everything like that. And you can translate that directly to the machine software. So consumables is another thing that goes into tube laser cutting, like just about everything else. There's a list of things that you're going to be burning through when you're cutting on a tube laser, and that need to be upkept, whether it's just a wear item or an accidental thing that you need to keep stock. There's definitely consumables to that as well. Oh, it might work this time. No.
Could you run those at the end, Marshall?
Just on
We've
that.
got somebody coming in to look at that.
Okay, sure. So essentially there I have a video that we talked about, multi-axis or 5-axis tube laser. That would be cutting a bent tube after it's already bent. And then a video of kind of your standard. I believe this laser has tilt capability, the 3D cutting capability, but it's a standard inline tube laser, meaning that you're loading raw straight lengths of material. So some challenges with tube laser cutting. There's a lot of aspects to creating a correct cut condition or a quality cut. One being focal position. So your focal position is basically where that beam of light is going to be focused to its finest point to ensure like your best quality cut. So if you're cutting a thicker material versus a thinner material, your focal position is going to have to change because you want that beam of light concentrated in the correct spot so you get that clean cut. Another thing would be weld seam detection. Kind of to your point about the weld seam splitting, the weld seam is critical for a bent part. So if you're laser cutting bent tubes ahead of time, and say there's features in there that you need to have oriented relative to that bend, you have to pay attention to where that weld seam is also. Most of the time, you're going to want that weld seam on a neutral axis being like the top or the bottom relative to your bend, your plane of bend. So there's not as much compression, there's not as much stress on that weld seam. So the other thing relative to weld seam is sometimes you get some nasty thick weld seams on tubing. If your laser is kind of on the edge of cutting through the material in a nice quality fashion, if sometimes it hits that weld seam could be quite a bit thicker than your material, and you may or may not lose that cut because it's trying to cut through so much extra material. So depending on your features that are going to be laser cut on that tube, you might want to try to keep it away from the weld seam if you can. Like if it's not going to be bent or anything like that, and it's not aesthetically critical to have a weld seam hidden or something, you might want to keep all features as far away from the weld seam as possible, just for that reason. Sometimes if you have a slot that's going to be running linearly down that weld seam, your slot might not actually cut out all the way. You might have parts of slugs getting stuck in the tube, which can be bad, especially if you're on high volume jobs and your operator's just watching parts flying out of the machine, and something happens like that. You might have rejects because you have slugs stuck in your tubing that nobody was going to catch. So nozzle size and gas pressure. Again, these are kind of all things that have to be dialed in relatively accurately to get a nice quality laser cut. So nozzle size would be relative to the opening and the bottom of the nozzle where your sys gas is going to be coming out, whether it's shop air, nitrogen, or oxygen, or argon for that matter. And your gas pressure is going to be the pressure of those said gases coming out of that nozzle. So your nozzle size and gas pressure again are going to be related to primarily the material you're cutting and the material size that you're cutting. If you're going to be cutting some thicker material, a lot of times you'll need a larger nozzle size to get that gas to evacuate all the molten material that laser's trying to cut. And then gas pressure as well, you need to have enough pressure to blow that molten material through. And also it acts to cool off the cut area, because if you're developing too much heat, that can affect your laser cut condition. You can have blowouts and things like that, and inaccuracy in certain features. Again, nozzle centering, relative to your nozzle size and your individual nozzle that gets screwed onto the bottom of the cutting head. And for those that you don't know, this would be your nozzle here. So this is your cutting head and this is your nozzle. All your laser is going to be coming straight through this nozzle, and then the hole on the bottom of the nozzle is also going to be allowing for your gases to flow through. So nozzle centering has to do with the laser beam itself coming through the center of that nozzle. If it's not quite on center and it's off to one side, it can kind of deflect the beam actually a little bit and ruin your cut condition. I've seen it where it's been off center, and if you do a standard cut off, one side looks great, and then the other side of the tube you might have a burr on it. And there's a couple operators that I worked with that were chasing their tail on, changing everything else in their tech table, focal position, pressure, speed, power, everything like that, but they didn't check their beam centering or their nozzle centering. And once the nozzle centering was dialed in, it was cutting great. So that's a pretty critical aspect that I think gets overlooked sometimes. Heat transfer, like I talked about, sometimes the gas can cool down the area around your cut feature. You don't want to have too much heat transfer due to potential issues like blowouts and bad cut quality. Sometimes if the part gets too hot, it'll actually turn more than just your desired kerf, which is just your, like a kerf on a saw is just your cut area itself. If the material around that gets too hot, it actually can become molten and get blown away too. So you want to do whatever you can to keep heat transfer down. One of the ways to kind of do that is adjusting your duty and frequency also. Some of the thicker materials where you might have these heat transfer problems, you can play with the duty and frequency on your laser. The duty is basically a duty cycle on like a lot of other electronic devices or like welders and things like that. You have essentially on and off time of that laser beam, and so if you have a high duty cycle, it's running more consistent, and it's also putting more heat in. Frequency, these lasers are essentially pulsing, So like if you have a high frequency, it's going to be pulsing faster. If you have a low frequency, it's going to be pulsing slower. That can affect like your cut edge, the quality of your cut edge. If you have a high frequency, you'll have a lot of very little faint thin lines on the edge of your material that you're cutting. Can be, depending on your material, can almost look like a machine finish. You can get some really good laser cut quality, especially with like a fiber optic laser. But on some of the thicker materials, you might have a lower duty or frequency, and you might see each of those like lines where the laser is actually cutting and blowing away the material. Power, that's pretty self-explanatory. Power is how much power the laser is put out. So power is typically in watts. So you can adjust how much wattage that laser is actually pushing through. For thicker materials, a lot of times you're going to have to use higher wattage. And then thinner material, you can use less wattage. Again, your power also feeds into your heat. So you're going to probably want to use the lowest power you can and get through your material with a quality cut, just to try to keep your heat down. And then replacement of consumables, kind of like I touched on before, consumables being wear parts or parts that you're going to have on hand to stock in case of small collisions and things like that. It's just for speed. It's not really for beveling or chamfering or anything like that. But so this is essentially one long streak of material, and it's just cutting parts off the one end. So I believe this is about 1/8 inch wall stainless material. Then the 5-axis tube laser. So this is a post bent part. Obviously, it's already bent. There's a cut already made on here for clearance. This is a 5-axis laser with a robotic handling arm.
Is that what gives its 5th axis then?
The 5th axis is just actually on the head itself.
It is.
Yep. So there's your Z axis, your X and Y, a rotation around your Z and a rotation around either your X and Y. That would be this axis coming off here. So I believe this machine is X, Y, Z, C, and B. It's actually considered. So like you said, I mean, it's obviously a separate machine from your bender, but it's something that you could go right from your bender to a machine like this. And it doesn't necessarily have to be a robotic arm. There's a lot of 5-axis cutting machines that work off of fixture tables, so you can fixture up your part and then have this 5-axis cutting head come down and cut the parts.
So is that thing scanning the part that it's cutting to know where the surface is at?
It's actually not. It does have a capacitance sensor where it can see how far the head is or the tip of the nozzle is from the material before it starts to cut. So it knows whether it's going to crash into the material or not.
That's always, so it's constantly monitoring as it's.
It is, yeah. And then you can establish like your set height if it doesn't see, within so many millimeters or however you have your configuration. It might either error out because it's not finding material, or if it touches the material, it error out because there's that low voltage electrical current running through it, and then it'll ground out on the material. At least in this machine's case, but I believe a lot of them are the same way.
Is the arm that's holding the part stationary during the cut?
It is in this point. Actually, it always is. It might have different locations.
The reason the arm exists is just to orient the part.
Exactly.
Probably for access.
Yep. So on this cut or this part, it gets everything in that one position. Obviously, here it didn't move at all. There was some extra material here. It probably extended out 2 or 3 inches that it cut in a different position, just slightly more tipped up. So this tangent wasn't on such an angle; it was more vertical. and it would come and cut this off so there was no collisions as this column rotated around the part. So that was 2 positions in 1 cut program. I believe it also had a dummy move in case this piece got stuck on there before it went from cutting this scrap off to the cut shown in the video. It would actually flip over and dump that piece of scrap off, so we didn't have any other collisions if that scrap hung on.
That Arndt's position in that obscure 3D angle, just to make sure that the cutting edge
Clear.
can really clear.
Yeah, exactly. It took quite a bit of programming time to get it dialed in there because we were pushing the limits on a couple of axes. Like that was probably the most difficult to get it in there and have everything else clear. This column, is maybe a 1/4 inch away
From that square section is pretty close to the top.
Yeah, exactly.
What part are they cutting? You know what that is?
What's that?
You know what part they're cutting?
Yeah, it's actually a heat shield for motorcycle exhaust. So it gets, 3/4 of the tube of this bent part is actually scrap, and all you get is the heat shield out of it. And it's just, I shouldn't say 3/4 of it, but it's just wrapped around more than half of the tube, so you can't use the other side.
How much programming time do you have in to get it to run this? Like something like this.
Sure. So programming itself, just trying to get the cut path established with no collisions in the software, probably 2 hours, something like that, 3 hours maybe. And then once you get to the machine, that's a little bit more complicated because you have to establish a location for that bent tube in the environment in every different position it makes. So like if there's 2 different cut positions, you have to establish a new origin twice. So it's a little complicated on something like this with the tube because you essentially have like a cylindrical origin you have to try to establish and get it to line up with your programmed origin, in any position that it's actually being cut in. But all said and done, I think programming and the machine setup to have this part actually run in 2 cells of the machine. So there's actually this is a divider, and there's actually another cell over here that cuts up your part. It was probably up and running in 6 hours, something like that. Fixturing is another thing for the robot to grab it. You have to take that into consideration because it's got to pick from the same point every time. So you got to have a nice solid fixture where your operator can load the parts in exactly the same way so it grabs it in the same spot. That's probably the most critical thing with this machine. And all of these CNC machines, as well as any vertical mill or anything like that, is your fixturing or your home position for your parts are very critical to the accuracy of everything. So that's a good example of something that you can do, or you can use a 5-axis tube laser in, referring to a bending kind of operation. They work pretty well hand in hand for something like that. I mean, that part also has 2 holes in it. I believe one hole is about a 1/4 inch off the tangency, so it's almost on the bend. There might be actually some bending going on, just that little bit, that 1/4 inch outside of the nominal tangency. So there's a little bit of deformation there. So theoretically, you could say it's probably on the bend, even though it's a hair off of it. But it puts a perfectly round hole, on a bend. So if you were to try to do that, like we talked about before you bent it, you probably wouldn't have any luck with it. We kind of talked a little bit about consumables. I would consider like a nozzle consumable because they do get smashed up every once in a while, whether it's intentional or not. It should never be intentional, but a piece like if a slug from a tipping hole or something like that comes up and hits it, that happens. And if it leaves just a little bit of mark or bars that hole at the very bottom of the nozzle, it might affect kind of how that laser or the gas is coming out. So you're going to want to make sure that's always nice and clean and a nice round hole. Working back up from that nozzle, there is porcelain insulator that also, if the machine has a capacitance sensor, that allows the electrical current to run through there. That's what actually the nozzles attaches to. So that's also, aside from being like an insulator for heat and electricity, it's also kind of made to break out of the way, so to stop direct impacts up through your cutting head. So then behind that, you have a protective glass. So that's like a very clean piece of glass. It's actually not exactly glass, but that's what they call it, glass. And your laser beam comes through that, and all that does is protect your actual focusing lens that's a little bit farther up in the head from anything reflecting back up or any dross that is slag that might be trying to make its way up through that little hole in your nozzle, because that does happen. And if you have a spot on your focusing lens, you're going to have some serious problems with cutting. So that's what your protective glass is in there for. And those are really the only consumables on the laser head section. And then obviously gas, your assist gas is going to be a consumable. Like I said before, you might have compressed air like shop air. A lot of companies are kind of transitioning to that. You just have to have real high PSI. Most standard air compressors don't compress to that PSI. I don't remember exactly, but you want to have about 400 PSI coming into the laser with shop air, as well as nitrogen. Oxygen can be a little bit less because you use less pressure. Oxygen would be used for thicker materials. It'll help it kind of burns away that material, where the nitrogen really just evacuates it and actually cools down the material around it. The oxygen kind of like works like a torch. You have that light coming through and then burning through the rest of that material. And then specifically, if you're cutting titanium, you're technically supposed to be using argon for gas. We've done very thin wall titanium cutting with nitrogen, and it's worked, but to get a good quality cut, argon is what you're supposed to be using. So that's kind of an overview of the consumables in laser cutting, whether it's inline laser cutting or 5-axis laser cutting.